Although structures like jets emit in the X-ray region of the spectrum, the X-ray band is dominated by the disk and corona, and so X-ray jet emission can be hard to detect in the region directly surrounding the black hole. Jet emission is more commonly associated with radio wavelengths. In this lesson, we will take a look at the spectrum of a black hole and see why this may be the case, and explore the mechanism that creates this emission, discovering what this can tell us about black hole systems. If we return to the plot we have been examining during this module, we can see the addition of this new radio component. From right to left, this new component begins in the same region of the plot as the spectrum of the disk and the corona. The overlap in this region of the spectrum is due to all three components emitting a portion of their energy in the X-ray band. The new radio component then extends to longer wavelengths or lower photon frequencies, peaking and then tailing off into radio frequencies. The jet of the black hole is responsible for this new component of the spectrum. Jets are powered by synchrotron radiation, energizing photons through interactions with electrons that are trapped in circular orbits around the magnetic fields within the jet. While we don't fully understand the mechanism that is used to launch the jet, astronomers suggest that the magnetic fields within the jet can be thought of as a tangled mess of spaghetti that has been stretched out in one direction. This stretched out spaghetti causes the jet to transfer energy and angular momentum into the surrounding area. Particles energized within the jet can extend out to incredibly large distances. Similar to the multicolored disk model, accurate descriptions of jets require us to consider smaller slices in order to account for the different energies supplied by the synchrotron emission. If the jet is cut up into narrow disks along its length, like slicing up a banana into small circular pieces, we can plot the spectrum of synchrotron emission from each of these disks. As we move away from the central black hole, the number of particles decreases, along with the strength of the magnetic field. By adding the contribution from each disk of the jet, we can recreate the spectrum of the jet. One mystery astronomers are trying to solve is why there appears to be two types of jets around black holes. The first type of jet is a continuous jet. And just like water spouting from the nozzle of a hose, the continuous jet is a continuous stream of particles constantly flowing outward along the path of the jet. The second type of jet has multiple names, but it is seen as clumps of particles being emitted out of the jet. Scientists call these clumps burps, bullets, or ejecta. Just like the continuous jet, jet ejecta provide a route for the spread of energy and angular momentum into the area surrounding a black hole. As a result, jets can sometimes be a mechanism to feed back energy into the region surrounding the black hole system. In this module, we have not yet considered how the orientation of the black hole system affects our observations. Since the jets tend to align with the spin axis of the black holes, the direction of their spin determines which way the jets point and how much light escapes. If we are viewing a black hole system with the accretion disk from the side, the jets appear to extend perpendicular to the center of the disk. If, on the other hand, we see the accretion disk from a top-down perspective, the jet is pointed directly at us and appears to be much brighter. This is because the emission is beamed towards us, increasing the energy of the photons we receive. If the system is at an intermediate angle, we will see a blue shift in the jet pointed towards us, while the jet angled away from us will be red shifted. We will also see that the jet angled in our direction is brighter than its counterpart. We should note that this difference in brightness and colour is due to the beaming effect. It does not mean that one jet is actually more powerful than the other, or that they're emitting at different wavelengths. If the jet is offset from the spin axis of the black hole, then we may be able to detect a wobble from the jet. This has been recently seen in observations of the black hole binary known as V404 SIG. A research team, including professors here at the University of Alberta, have been looking at V404 SIG to investigate its jet in more detail.